Welcome to Tales from the Periodic Table. I'm your host, Ron Hipschman, and today we're going to talk about the sixth element in the periodic table, carbon. Now, normally when I show you elements, I have a little tiny vial with a little tiny sample of the element in it. But today, since carbon is such a common element, I have it in many forms. For instance, here I have carbon in the form of a charcoal briquette that you might use in your barbecue, or carbon in the form of coal, and this you might get in your stocking at Christmas if you're a bad boy or girl. Or you might have graphite in your pencil. This is yet another form of carbon. Thank you, Phil, for acquiring this giant piece of it for me. And you might find carbon even in a crystalline form, like in this diamond right here. Now, obviously, this is not a diamond. If this was actually a diamond, I wouldn't be doing Tales from the Periodic Table. I would be relaxing on a beach in the Caribbean. If you stick with me, by the way, to the end of this video, I have a treat for you, a wonderful and appropriate song for today's element. Here we see the beautiful periodic table produced by Theodore Gray. As I've mentioned in previous episodes, Theo has written one of my favorite books called The Elements, which I encourage you to pick up. Check out his fantastic website, periodictable.com. Carbon is the sixth element in the periodic table. Its atomic number is 6 because that's how many protons are in its nucleus, and that is what distinguishes it as a unique element. 11 elements were discovered prehistorically. Certainly, carbon tops this list with its appearance every time something is burned. However, that doesn't mean it was recognized as an element prehistorically. And while I'm pointing out things in the periodic table, carbon is one of 14 elements with single-letter designations. I know, a pointless factoid, but I like it nonetheless. But back to carbon. Carbon is one of those elements discovered prehistorically because it sits in its native form as coal and graphite in many places on Earth. Of course, it also occurs naturally as diamond, but perhaps not as easily found. More on this in a bit. The great French chemist Antoine Lavoisier was the first to declare carbon an element in 1789. In one of the great tragedies in science, he was put to the guillotine at the early age of 50 during the French Revolution. The great Italian mathematician, physicist, and astronomer Joseph Louis Lagrange lamented, "It took only an instant to cut off this head, and 100 years might not suffice to reproduce its like." Carbon is certainly one of the cheapest elements around, at least if you're talking about it in the form of coal. Coal costs pennies per kilogram. In the form of more refined graphite, the cost rises to about $1 per kilogram. In the form of synthetic industrial diamonds, you'll pay between $1,200 and $13,000 for a kilogram. Gem-quality diamonds are variable in cost per weight, and it depends on the size of the stone. Bigger stones are much more expensive kilogram for kilogram, or in diamond units, carat for carat. By the way, a carat is 1/5 of a gram, or only 7/1000ths of an ounce if you insist. Let's use a standard 1-carat diamond as a starting point. There are 5,000 carats per kilogram. Your basic 1-carat diamond is about $4,000. So that calculates out to a stunning $20 million per kilogram. Certainly one of the most expensive of the elements, at least in the form of diamond. Carbon is considered a non-metal, though it does have a few qualities that metals possess, such as electrical and thermal conductivity. The element carbon is very common in the universe, coming in as the 4th most abundant element by mass. 0.5% of the universe is carbon. That's 1 atom out of every 200. It's also the 4th most abundant element in the Sun, making up 0.3%, or about 1 in 300 atoms. It's the seventh most abundant element in meteorites, 1.5% of their makeup. There's a whole class of meteorites called carbonaceous chondrites that can contain up to 3% carbon. It's 0.18% of the crust of the Earth, that's 1 in 550 atoms, the 10th most abundant. Carbon is the 9th most abundant element in the oceans, at about 1 out of every 36,000 atoms, only 0.0028%, but that's still a lot compared to other elements. And lastly, and maybe not surprisingly, being a carbon-based life form, carbon is the second most abundant element in us, making up 23% of our body's mass. Each element has many different forms. For each specific element, the number of protons in the nucleus is the same, 6 protons for carbon. But there can be different numbers of neutrons in the nucleus. All these different forms are called isotopes. They're chemically identical to each other, but with slightly different weights. The number you see next to the chemical symbol is the total number of protons and neutrons in the nucleus. There are 15 known isotopes of carbon, and of these 15, there are 2 stable non-radioactive isotopes, carbon-12 and carbon-13. Carbon-12 makes up the vast majority of carbon in the universe, 98.93% of it. The remaining 1.07% is the slightly heavier carbon-13. By the way, the word isotope comes from the Greek, isos, meaning same or equal, and topos, meaning place, since all these various forms of carbon occupy the same place in the periodic table. Of the radioactive isotopes of carbon, these are the ones with half-lives over 1 second. The longest-lived isotope, carbon-14, has a half-life of 5,700 years. More on half-life in the next slide, and we'll be seeing more of this isotope in a bit. What's a half-life? This graph shows an exponential decreasing curve. As an example, let's say we start with 1,024 atoms of any isotope. You'll see why I chose 1,024 atoms. Hint, it's a power of 2, and we're going to be doing a lot of dividing by 2. If we wait 1 half-life, half of our isotope will decay, and we'll have 512 atoms left. If we wait 1 more half-life, half of that half decays, leaving us with 1/4 of the original 1,024, or 256 atoms. Another half-life, half again as many, or 128 atoms, and so on. We just keep dividing by 2 every half-life. After 10 half-lives, we'll have about 1/1000th of our original amount. By the way, notice that there's 1 remaining atom after 10 half-lives here. If we waited 1 more half-life, our remaining atom would have a 50-50 chance of decaying in that time. It's a bit hard to pin down the density of carbon because it appears in many forms, or allotropes. More on that in a bit. However, pure graphite has a density of 2.267 grams per cubic centimeter. Diamond is slightly denser, at 3.515 grams per cubic centimeter. Remember that the density of water is 1 gram per cubic centimeter, and I've put up a few more densities here for you. Graphite is slightly less dense than aluminum, and diamond is slightly more dense. Here's a graph of the elements from highest density to lowest density. I have a set of blocks so you can feel density for yourself. My set of blocks have a wide range of densities, with the densest at tungsten, to lead, to copper, to iron, to titanium, to aluminum, to magnesium. I also have plastic and wood blocks, but those are not technically elements. Again, carbon's density is 2.267 grams per cubic centimeter in graphite form. The magenta circle, a little denser than magnesium. Again, in the form of diamond, it has a slightly higher density of 3.515 grams per cubic centimeter, about the same as barium. Carbon as graphite does not technically melt. At a temperature of around 3,600 degrees Celsius, or 6,512 degrees Fahrenheit, it turns directly into a gas, or, in other words, sublimes. Obviously, this has to be done in an oxygen-free environment, otherwise the carbon burns and becomes carbon dioxide. If we compare the size of the carbon atom to that of hydrogen, we'd see something like this. The carbon atom is a little more than twice the size of hydrogen. Notice the 4 electrons in the outer shell. We'll get to them. By the way, a picometer is a trillionth of a meter. Atoms are shockingly small. Here are atom sizes sorted from largest, cesium, on the top left, to smallest, helium, on the bottom right. Carbon has the 7th smallest sized atom of the elements. Carbon in the form of graphite is a very soft element, coming in at 0.5 on Mohs scale of hardness, a lot softer than your fingernail at 2.5. In diamond form, it's the hardest known element at 10. Related closely to its hardness is its springiness, and carbon in the form of diamond is really stiff, springy stuff. Sound, therefore, moves through carbon really fast. It's the fastest element. Sound moves through diamond at an astonishing 18.35 kilometers per second, 53.5 times as fast as sound moves through air. You can build different forms of a pure element structurally. These are called allotropes. They're all pure carbon, but with different arrangements of their atoms. This is the arrangement of the carbon atoms in a diamond, where every atom is connected to 4 other atoms in a tetrahedral arrangement. Very strong. In graphite, the atoms are arranged in hexagonal sheets with very weak atomic bonds between the sheets. This is yet another arrangement you'd find in the mineral Lonsdaleite. These 3, with 60, 540, and 70 carbon atoms, form spherical-like structures called fullerenes. When carbon atoms join willy-nilly with no structure, you have amorphous carbon. Lastly, you can take graphite sheets and make cylinders. These are called carbon nanotubes. Let's take a look at a few of these from a more human scale. The main allotrope we encounter is amorphous carbon in the form of coal. The atoms have no orderly arrangement. Graphite has a semi-crystalline structure with hexagonally arranged atoms in flat sheets loosely connected together. Notice that graphite has a shiny, almost metallic sheen. This is a special crystalline form called pyrolytic graphite. The hexagonal arranged carbon atoms are layered and bonded in a more orderly fashion. It's like ordinary graphite, but with better alignment of the atoms between the layers. Diverting for a bit, diamagnetism is an effect where magnetic fields are repelled. In most elements, the attractive force overwhelms the repulsive force, but in carbon, in this case the pyrolytic graphite from the previous slide, the force is strong, and it actually floats above the magnets. Absolutely remarkable. The next allotrope is the extremely tightly bonded diamond. This is a low-grade diamond in its natural state with very poor optical qualities. It will probably be ground to dust and used industrially as an abrasive. These pretty little yellow crystals are entirely human-made synthetic diamonds. They're pretty small, not quite a powder, but not exactly something you could make a ring from. About 30% of all industrial diamonds in the United States are artificially made. These are uncut cubic Congo diamonds. You'll never guess where they were mined. And while we're still on the subject of where diamonds are mined, their production is limited to only a few places on Earth, mainly found in Africa, specifically South Africa, Namibia, Botswana, the Republic of the Congo, and Sierra Leone. Diamonds are also found in Canada, the Russian Arctic, Brazil, and Australia. Graphene, closely related to graphite, is another allotrope. It's an extremely well-ordered, flat sheet of hexagonally arranged carbon atoms, but it's made to have only a single sheet of atoms. It's a recent invention. In 2004, the material was rediscovered, isolated, and investigated at the University of Manchester. It normally looks like a very black powder. You might not even be able to see it, it's so black. A single layer of graphene is transparent and can be made into a flexible conductor that holds great promise for various material and device applications, including solar cells, light-emitting diodes, integrated circuits that use light instead of electricity, called photonics, touch panels, smart windows, and phones. Smartphone products with graphene touchscreens are already on the market. Roll a graphene sheet into a tube and you get carbon nanotubes. Some carbon nanotubes can exhibit remarkable electrical conductivity, while others are semiconductors. They also have exceptional tensile strength and thermal conductivity. We're only beginning to find out uses for these unique structures. Fullerenes are geodesic dome-shaped carbon molecules, named after, of course, Buckminster Fuller, the architect who popularized the geodesic dome. Let's look at a tiny bit of carbon chemistry, often called organic chemistry. We're not going to even scratch the surface here. Many people spend their entire lives researching even tiny corners of this vast chemical discipline. Carbon has 4 valence electrons available for chemical bonds. Let's look at it with a ball and stick model. Carbon is very versatile, using these 4 possible bonding sites. For instance, you could attach one atom to each available bonding site. If you attach hydrogens, you get CH4, or methane. This comes out of your gas stove, and you burn it to cook your food. Sometimes the bonds can pair up and attach to other double valence atoms, like a couple of oxygen atoms. That gives you CO2, or carbon dioxide. There are almost infinite possibilities. Carbon and hydrogen can form into long chains, or hydrocarbons. Throw in an occasional oxygen, and you can make alcohols or sugars. You can also make acids, and with a few nitrogen atoms, create the acids that make up the basis of all life, the amino acids. Lipids are a broad group of naturally occurring molecules which include fats, waxes, sterols, fat-soluble vitamins such as vitamins A, D, E, and K, monoglycerides, diglycerides, phospholipids, and others. Carbon participates in a process within the sun that combines hydrogen into helium, powering the star. This is called the CNO cycle for carbon, nitrogen, oxygen. This occurs in the sun and at even higher rates in somewhat larger stars. Just for fun, let's step through that process. Note that we're only going to talk about nuclei here because at the temperature inside the star, the electrons are stripped from the atoms and become part of the general plasma. Carbon-12 combines with a hydrogen and makes nitrogen-13. That 1.95 MeV, or million electron volt, is energy given off in the process as a gamma ray. The nitrogen-13 is itself radioactive and decays, giving up a positron and some energy, becoming carbon-13. The carbon-13 fuses with another hydrogen, becoming nitrogen-14. Energy is given off as a gamma ray. The nitrogen-14 combines with yet another hydrogen, becoming oxygen-15, and more energy as a gamma ray. Oxygen-15 is radioactive, emitting a positron with some energy, becoming nitrogen-15. And finally, the nitrogen-15 fuses with a hydrogen, resulting in one atom of carbon-12 and one of helium-4. Note, in this whole process, we've consumed 4 hydrogen atoms, in red, and produced a helium atom, in blue. And we've recovered our slightly used, or should I say pre-owned, carbon-12 atom, which can now be recycled back into the process all over again. No carbon was harmed in the process of turning hydrogen into helium, producing energy. There's also a carbon cycle right here on Earth, except here we're talking mainly about carbon dioxide, CO2. It's a complicated set of interactions, as you can see from this slide. CO2 is held not only in the atmosphere, but also in the oceans and vegetation, both on land and in the sea. It's also stored underground in minerals and fossil fuels. CO2 circulates to and from many of these sources and sinks. Looking at the atmosphere, we've been burning fossil fuel from time immemorial. But since the Industrial Revolution, that burning has accelerated dramatically to the point where the rest of the environment can't keep up with our CO2 emissions, and it's now building up in the atmosphere. We are now affecting the entire planet. In 1958, Charles Keeling started collecting data from the slopes of the Mauna Loa volcano on the Big Island of Hawaii. Here, he established an atmospheric observatory. He reasoned this location at over 11,000 feet was ideal to measure atmospheric gases, being high up and located in the middle of an ocean, pretty much away from civilization. Keeling thought it was important to monitor atmospheric gases, especially CO2. When I visited the lab in 2012 to webcast the transit of Venus across the face of the Sun, notice the telescopes, I obtained a sample of the air at that time. Notice the concentration of CO2 was 395.15 parts per million. We'll come back to this number in the next slide. The lab at the site now bears Keeling's name. I want to concentrate a bit on that graph you see on the plaque. This graph shows the change in atmospheric CO2 over time. As you can see, the amount of CO2 has increased dramatically since 1958, when Keeling first started measuring its concentration. As a matter of fact, this is now called the Keeling curve. The small up and down variations on the red curve are seasonal and caused by winter die-off and spring growth of vegetation. During my visit in 2012, the concentration of CO2 was 395.15 parts per million. In 2023, it's at 419 parts per million, 6% greater in just 11 years. Carbon, in the form of CO2, is a serious problem which is posing an existential threat to the planet. One can debate the politics, but the data is not up for discussion, period. In case you're thinking this may be part of some normal and natural cycle, here's the CO2 record over the past 800,000 years, taken mainly from ice cores. While there are ups and downs as ice ages come and go, the broad average was between 200 and 250 parts per million, with a previous high at 300 parts per million about 325,000 years ago. Even compared with that historical record, we're off the charts today at 419 parts per million in 2023. And speaking about looking into the past, we need to talk a bit about an extremely important application: carbon dating. There are three important isotopes that come into play here: carbon-12, 13, and 14. We'll just concentrate on carbon-12 and 14 for now. The radioactive carbon-14 decays by giving off a beta particle, an electron, from its nucleus. This transforms it into nitrogen-14, the stuff you're breathing right now. That other particle is a neutrino and doesn't really enter our discussion. I include it for completeness. Carbon-14 was discovered at UC Berkeley in 1940 by Martin Kamen and Sam Rubin. Willard Libby at the University of Chicago accurately measured the half-life of carbon in 1949. His accurate figure of 5,700 years enabled the scientific community to use carbon-14 as a method to date biological material. With carbon-14 decaying all the time, after billions of years on the Earth, it should, for the most part, be gone. However, it's being continuously manufactured in the atmosphere by cosmic ray bombardment of nitrogen molecules. This is a process called spallation. Because of this, there is more or less a constant amount in the atmosphere. This newly made carbon-14 combines with oxygen and becomes CO2, carbon dioxide, which is absorbed into water, becoming part of the aquatic ecosystem. It's also absorbed by plants, which are then eaten by animals. So everything has a constant amount of carbon-14. That is, until you, or a plant or an animal, dies. Then your intake of CO2 stops and the carbon-14 begins to decay away. Remember this graph from earlier? Let's quickly review. As carbon-14 decays in your now dead body, with its 5,700-year half-life, there is less and less of it compared to the stable carbon-12. Like before, if we start with 1,024 atoms of carbon-14, after 5,700 years, one half-life, there's only half left, or 512 atoms. Another 5,700 years, half of that half remains, or 256 atoms. Another 5,700 years, 128 atoms, and so on. So over time, there's less and less carbon-14 compared to carbon-12, which is not decaying. Now, we just have to follow a few steps to determine how long the thing you're measuring has been dead. First, you measure the mass of the sample. From that, you can determine the total number of carbon atoms. Then, we measure the radioactivity of the sample. That will give us the number of carbon-14 atoms in the sample. And lastly, we calculate the ratio of carbon-12 to carbon-14, and that gives us the age of the sample. This only works for things that absorb carbon while they're alive. This method is usable out to about 10 half-lives, or about 60,000 years. Let's look at a few more applications of carbon. In the form of charcoal, carbon is used as a source of fuel for heating and cooking. Charcoal is made by heating wood without much oxygen. Joseph Swan, a British physicist, used the fact that carbon conducts electricity. When you pass electricity through it, it heats up and glows. Unfortunately, hot carbon quickly combines with oxygen in the atmosphere and vaporizes. He worked out a way to put this glowing carbon thread or filament inside an evacuated glass envelope with no air, and presto, the electric lamp was born. He first demonstrated this in 1860, but it didn't become practical until about 1880. While Joseph Swan worked in Britain, Thomas Edison was simultaneously doing the same work in the United States. He first demonstrated his team's invention in October 1879. They were the first electric light bulbs in the U.S. and became available commercially that same year. Edison is responsible for the screw base that we still use today in the U.S. Lewis Latimer first worked as a draftsman for Alexander Graham Bell and produced the patent drawings for the first telephone. But his most significant contribution was in improving the incandescent light bulb. By figuring out how to more efficiently produce longer-lasting carbon filaments for the bulb in 1881, he made electric lighting more practical and affordable for the general public. He contributed greatly to Thomas Edison's work, though usually he remains uncredited. He was also an advocate for civil rights and co-founded the Flushing, New York Unitarian Universalist Church. Encase graphite rods in copper and pass electricity through them in the form of an arc, and you can use carbon to weld metal together, or, with a continuous jet of air, you can melt metal and blow it away, effectively gouging and removing metal. Kind of opposite what you normally do when you weld. The lead in your pencil is not lead at all, but rather graphite. The slippery sheets of carbon atoms in graphite easily slough off onto the paper. Here is a graphite casting mold to make metal hemispheres, one to cast metal ingots, and if you want to make your own pirate doubloons, you can carve a mold from very soft graphite and have at it. Remember, carbon does not melt or vaporize at any temperatures lower than any other element. It's an ideal material to make casting molds from. You can also make crucibles for melting substances at very high temperatures, but you have to be careful not to have too much oxygen around these when they're hot. Carbon fiber is made of thin, strong, crystalline filaments of carbon that are used to strengthen material. The carbon fiber can be thinner than a human hair. It gets its strength when twisted together like yarn. Then it can be woven together to form cloth, and if needed to make a permanent shape, carbon fiber can be laid over a mold and coated in resin or plastic. Carbon fiber is 5 times stronger than steel and twice as stiff, but much lighter. To go over its properties, it's stiff. It has high tensile strength, resistant to stretching. It's light, yet strong, is chemically resistant, temperature resistant, and does not expand much with temperature. It's a pretty ideal material. You'll find carbon fiber used almost everywhere, from tennis rackets to bicycles, and of course in the automotive industry for car parts like steering wheels and motorcycle helmets, and even whole cars if you have the cash to afford this ridiculous Lamborghini, and I'm barely scratching the surface here. Scientists often want to squeeze something to see how it reacts under pressure. If you want extreme pressure, you squeeze between 2 diamonds in a device called a diamond anvil. Here's a cutaway side view. With the small surface area and the strength and hardness of diamond, you can reach pressures of 7.7 million atmospheres. Since you can see through diamonds with light, you can monitor what's happening. If you want to know about processes happening at the pressures found in the center of planets, the diamond anvil is your friend. Industrial-grade diamonds are embedded in a matrix of relatively soft iron. The gaps here are to allow the chips to escape, and possibly for cooling fluid as well. Likewise, you can buy yourself a diamond-encrusted sharpening stone to sharpen your cutlery. The diamonds are embedded in the metal, not the recessed holes which provide a place for the metal chips to sit. Sometimes diamond powder in a liquid is used to grind and polish optics. This suspension contains diamonds only 6 microns, 1/10 the width of a human hair in diameter. Sort of opposite the previous slides, powdered graphite is the recommended lubricant for locks and other mechanical systems where oil and grease would not be appropriate. Oil and greases not only attract dust and dirt, but also become more viscous at lower temperatures. Graphite does not have a temperature problem. Your body is a huge user of carbon. You wouldn't exist without it. As I mentioned before, carbon makes up 23% of your body by weight. We are carbon-based life forms. However, carbon in the wrong places in your body isn't healthy. Here we see a section from the lung of a heavy smoker. Notice the multiple cavities lined by heavy black carbon deposits. Listen to the Surgeon General. As usual, with all of my talks, we'll end with Mary Soon Lee's elemental haiku about carbon. Show-stealing diva, throw yourself at anyone, decked out in diamonds. In the next program in this series, we'll examine a gas you inhale with every breath you take, nitrogen. I hope you'll join me. I'm your host, Ron Hipschman. Thank you for watching this Tales from the Periodic Table program about the element carbon. As I promised, now I present to you my good friend Linda Williams and her original presentation of Carbon is a Girl's Best Friend. Enjoy.
A lithium dose just might cure your depression, but carbon is a girl's best friend. And gold may be grand, but it won't start a fire in your barbecue or put the toot in your choo-choo, 'cause life on Earth is carbon-based. It came here on rocks from outer space and formed organic compounds till the carbon cycle went round and round. Carbon is a girl's best friend. Well, there may come a time when you need to do some squeezing. Carbon is the world's hardest friend. And there may come a time when a substrate is needed to deposit your film on. Just sputter it on a hot diamond, or if you have some lube and to do, then graphite is the allotrope for you. Or if you're into ages, then carbon-14 can date it. Carbon is a girl's best friend. Well, I've heard of attempts to make hard carbon nitrides, but diamonds always win in the end. You know they do, darling. And I've heard that we need to find something much cleaner to put into our cars, or else we won't get very far, 'cause time rolls on and supplies will be gone of diamonds, coal and petroleum. But nanotechnology can build anything with fullerenes. Carbon! Carbon, yeah! I don't mean hydrogen, but carbon is a girl's best friend. Best